Today we're going to be talking about exponential functions. Now, there are two types of exponential functions that we can have. We can have an exponential growth function, or we can have an exponential decay function. First, let's start with our exponential growth function. So, our exponential growth function is defined by f of x is equal to b to the x when b is greater than 1. Now, this is important. Our exponential growth function is only a growth function when b is greater than 1. Alright? So, let's take a look at our example that we have right here. We can tell that this is an exponential growth function since we have 2 as our base, which we know is greater than 1. So this is indeed an exponential growth function. Now let's fill in our table. When we put negative 1 in for x here, we get as our y value 1/2. When we put 0 in for our x function here, we get as our y value 1. When we put 1 in for our x value here, we get as our y value 2. When we put 2 in for our x value here, we get for our y value 4. Now that we have everything put into our table on the left, let's graph our points on the right. We have a point at negative 1, 1/2, a point at 0, 1, a point at 1, 2, and a point at 2, 4. And now we have our function. Now that we have our function graph, let's look at some characteristics of our exponential growth function. So, its shape is growing. You can see that our function over here is always growing. Our domain is all reals. You can see that for every x value possible, there is always going to be a y value. Our range is y is greater than 0. You can see with our function here that our function never touches the negative part of the y-axis. However, if our function is transformed, then we know that our range can change, and y is just always going to be greater than our k. Here's the general form of our function. This is how it can be transformed. Now, our asymptote is horizontal, and just like the range, it can also be transformed if there is a different k. So our asymptote is y equals 0 if it's a simple function like this, or y equals k if it is a transformed function. Our end behavior is the horizontal asymptote. It is always approaching the horizontal asymptote. Our function is increasing everywhere and decreasing never. This is important because this is a characteristic that only holds true for exponential growth and does not hold true for exponential decay. Our x-intercepts are none. You can see that our function never crosses the x-axis. Our y-intercept is 0, 1, which you can see in our table here, and you can also see on our graph here. Our exact points are negative 1, 1/2, 0, 1, and 1, 2, which are only just a few of the very many exact points that you could have for this function. Now let's move on and let's talk about exponential decay. Now, exponential decay is defined by f of x is equal to b to the x when b is between 0 and 1. Now, this is important. Exponential decay is when b is between 0 and 1. We can tell that our function right here on our table is an exponential decay function since 1/2 is between 0 and 1. Now let's fill in the points on our table. When we put negative 1 in for our function here, we get as our y 2. When we put 0 in for our function here, we get as our value 1. When we put 1 in for our x value here, we get a value of 1/2. When we put 2 in for our x value here, we get a value of 1/4. Now let's graph our points on the table on the right. We have a point of negative 1, 2. We have a point of 0, 1. We have a point of 1, 1/2. And we have a point of 2, 1/4. And we can now graph our function. Now let's talk about some characteristics. Our shape is decay. Our function is decaying, it's going down. Our domain is all real numbers. You can see that for all x's we have a value of y. Our range is y is greater than 0 or y is greater than k. Same as before, this is depending on if our function is transformed or not. Our asymptote is y is equal to 0 or y is equal to k for that same reason. Our end behavior is that it is always approaching our horizontal asymptote. Now this is where things get to change a little bit. Our decaying function is increasing never and decreasing everywhere. This is the opposite of our exponential growth function. Our x-intercepts are none. Our y-intercept is 0, 1. And our exact points are -1, 2, 0, 1, and 1, 1/2. And like as before, these are only a few of the very many exact points that you could have for this function. Determine if each function is an exponential growth, exponential decay, or not an exponential function at all. Explain your reasoning. So, we know this first one is going to be an exponential growing function since our base is greater than 1. We can see in our second one that this is going to be an exponential decaying function since our base is less than 1. You can see that this does not have any number raised to an exponent that is a variable. This is a line. So this is going to be neither, because there is no variable in the exponent. I want you to pause this video here and try the next 3 on your own. You can see that our base here is a decaying function because our base is less than 1. You can see here that our base 11 is greater than 1, so this is a growth exponential function. You can see our base here is less than 1, so this is a decaying exponential function since b is less than 1. You can see that our base here is greater than 1, so this is a growth function because b is greater than 1. Now, this is where things start to get a little bit different. When we have a base that's raised to a negative exponent, the outcome is going to be the opposite of what it normally is. Let's think about this logistically. We know 4 raised to the negative x power is the same thing as 1/4 raised to the x. This then makes our base less than 1. So this is a decaying exponential function since b is less than 1. You can see here that we have a base that's originally less than 1, but when we flip our exponent to be 1 over 0.45 raised to the x, this is the same thing as 2 to the (100/45), which is indeed greater than 1. Since our base is greater than 1, this is a growth exponential function since b is greater than 1. Now let's move on to the next example. State the domain, range, and horizontal asymptote of each function. Let's look at our first function. You can see that our function is transformed and it is going up by 4. Our domain is all real numbers. Since our function is going up by 4, our range becomes y is greater than 4. our horizontal asymptote is going to be y is equal to 4 because of this transformation. Now let's look at our next one. Let's look at b. We can see that our function is being brought down 8. Our function is always going to be all real numbers, so the fact that we have an x plus 2 here doesn't change what our domain is going to be. This, however, does change our range, just like it did in the previous problem. Our range is going to be y is greater than negative 8. Our horizontal asymptote is y is equal to negative 8. I want you to pause this video now and try the next two on your own. Now let's look at our next problem. We can see that this function is being brought down by 12. Our domain is still going to be all real numbers. However, now our range is going to be y is greater than negative 12. Our horizontal asymptote is y is equal to negative 12. Now let's look at our next one. We can see that our function is being brought up by 2. We know our domain will stay the same. Our range is now going to be y is greater than 2, and our horizontal asymptote is going to be y is equal to 2. Now let's go on to our next example. Graph each function. Make a table of points for each transformation. State the domain, range, and horizontal asymptote. Our domain is going to be all reals. We can see that our new range is going to be y is greater than negative 4, and our horizontal asymptote is going to be y is equal to negative 4. For our table, we're going to test some random points. The best points to test are the points that are around numbers that are going to make our exponent equal to 0. So I'm going to test 0, 1, and 2. When I put 0 in for my exponential function, I get negative 3. When I put 1 in for our exponential function, I get negative 1. When I put 2 in for our exponential function, I get 5. I know I have an asymptote at y is equal to negative 4. And I now have some points that I can plot on my graph. I have a point at 0, negative 3, a point at 1, negative 1, a point at 2, 5. And I could now plot my function. Now let's look at. Try 5b on your own. Pause the video here. This is what you should have gotten for 5b. Our domain is always going to stay the same. Our domain for this function is going to be all real numbers. Since we have this plus 3 at the end, we know our range is going to be y is greater than 3, which makes our asymptote y is equal to 3. We're going to choose x values for the table right near what makes your exponent equal to 0. In this particular problem, the point that makes our exponent equal to 0 is 1. So we're going to want to choose some numbers around that. So, our table. I'm going to choose the points 1, 2, and 3. When I put 1 in for my function, I'm going to get 4. When I put 2 in for my function, I'm going to get 5. When I put 3 into my function, I'm going to get 7. Now let's plot my points. I know I have a horizontal asymptote at y is equal to 3. I also know I have a point at 1, 4, 2, 5, and 3, 7. And I can now plot my graph. Try 5D on your own. Pause the video here. this is what you should have gotten for 5D.